Hi, my name is Andrew Bells, and something that confused me for a while was the epoxide reactions. Now, the mechanism for creating an epoxide was not too difficult. It's pretty simple, take an alkene and make an epoxide with carboxylic acid. You can draw here, it's a concerted step, which I can see where you would struggle at first, where the arrows would go and whatnot, but that in itself is relatively simple. And I'm just showing you this to remind you how to get an epoxide from an alkene, because what's more likely is that on a test, you would be given an alkene and then you need to get a diol. And then, so you need to be able to recognize that first I need to create an epoxide, and then I'm gonna have to react it through the mechanisms I'm gonna show you in a minute. And recognizing that is half the battle, but you also need to be able to show the mechanisms for how it happens. And there's two different mechanisms we focus on, and which one comes into play which time is kind of more up for you to memorize. So we know by using water as a solvent, a diol can be formed from an epoxide, but what is the mechanism for that? Are there multiple mechanisms for that, and why? What's driving that mechanism? So the mechanism depends on whether the solution it is in is acidic or basic, and I'll show you how that comes into play right now. So if we have an acidic solution, obviously there's going to be a higher concentration of hydronium ions, right? So what's likely is that the epoxide will get protonated and we'll end up with this this intermediate. So we have to consider the resonance in form of the ion in order to know which carbon the nucleophile will attack. And so it's not what you would initially think. Initially, you would think that it would attack the less sterically hindered carbon. But since there's resonance considerations, we have to see that the resonance structure A that I have drawn is going to be much more stable than the resonance structure B that I drew, because it has the plus charge on a tertiary carbon instead of a secondary carbon. So therefore, we can consider that A will have the greater partial positive on the more substituted carbon. So knowing this, we'll know that our nucleophile, which is it wants a plus charge, it's a nucleophile, is going to attack the more substituted carbon. So it does just that, and in doing so forms a alcohol with a water coming off the more substituted side, and then a simple deprotonation will lead to not only the diol, but also the acid being regenerated. So we get a diol as a final product, and notice here we got an alcohol and then a methyl coming off the less substituted, and then two methyls and an alcohol coming off the more substituted. So that's the mechanism for the addition reaction in acid for an epoxide. So in base, it's a lot more simple. It's a lot more intuitive. The hydroxide ion will attack the less sterically hindered side. So that's because there is no plus charge, so there is no resonance that we have to consider. So as opposed to the mechanism in acid, which is driven by resonance considerations and the fact that the more substituted carbon will have a higher partial positive charge on it, this one is simply driven by steric hindrance, which is much simpler, much more intuitive, and much more in line with what we have experienced before. So by a simple SN2 reaction, the hydroxide is going to replace one of the bonds of the that is attached to the epoxide oxygen. We're then given an oxygen anion there, and then that will deprotonate the water very easily, regenerating our base, ROH minus, and giving us an epoxide with one alcohol group, a methyl, and one alcohol group and 2 methyls on the other side. So that's pretty simple. So some final remarks is that notice that the epoxide additions in both acid and base yielded the same diol. It's an important thing to remember. So we got the two, like we just went over, we got the two different sides, one with 1 methyl and one with 2 methyls, and they both have 1 alcohol group. So if you were to get a multiple choice question that said, compare the final products from these 2 reactions, and you got epoxide additions and it showed it in base and it showed it in acid, you should know that it gives the exact same thing. And so that's just an important thing to keep in mind. It's not about the product. That's an easy thing to memorize. You put alcohol on both sides, but it's about how to get there. So another important note is that this mechanism is very similar to that of the X2 addition reactions and oxymercuration reactions. And so if you understand these truly well, you will understand the oxymercuration and X2 addition reactions really well. And so you can use this, the knowledge you've gained here, and apply it to the oxymercuration reactions and the X2 addition reactions. And if you're able to do all of those without any help, then great. You've got it. You've memorized everything. Not only do you not have to worry about the epoxide mechanisms anymore, you've got it, but you also will have understood these. And so this could be a great test for you to make sure that you understand everything. Notice, though, obviously you will not get a diol from either of these, not normally, but you'll get the normal products through the mechanism. The mechanisms mirror each other very well. So I hope that you've learned a lot in this video and that you can take it and apply it, and that it'll help you further down the line in your chemistry career.